Casting is one of the oldest manufacturing processes known to man. Many of the same techniques used today to produce high-precision parts for jet engines have been used by different cultures for thousands of years. A form of investment casting using a ceramic mold was used by the Chinese 3,000 years ago to make jewelry. Sand casting was used by the ancient Egyptians. Though casting has grown a great deal more sophisticated over the years, the basic concept is the same. A liquid material, usually metal, is poured into a cavity or mold of the desired form and permitted to solidify. Thus, in a single step, simple or complex shapes can be made from any material that can be melted. Castings can be as small as individual zipper teeth, weighing a fraction of an ounce, or as large as huge frames for ships, weighing hundreds of tons. Today, casting is one of the most widespread manufacturing techniques. Almost all casting processes consist of 8 main elements. The crucible is a vessel or pot in which metal can be melted and contained. Crucibles are generally made from heat-resistant substances such as ceramic materials. Metal crucibles can be used, provided that the melting points of the two metals are not very close. The pattern is a form of wood, metal, wax, or other material, around which a molding material is placed to make a mold for casting. Patterns are usually custom machined or cast. The mold is a form which contains the cavity into which molten metal is poured to produce a casting of definite shape and outline. These are produced using various processes. Molds may be either reusable, as in the case of permanent mold and die casting, or broken apart and discarded after each part is produced, as in the case of investment and sand casting. Most metals decrease in volume when they go from a liquid to a solid state. They also contract when cooled to room temperature. Consequently, the initial mold cavity must be larger than the final desired shape by what can be called a shrink factor, or a pattern maker's allowance. In the case of investment casting, an appropriate shrinkage factor would be about 2%. The core is a specially formed material which is inserted into a mold to shape the interior of a casting. A core is supported at either end by core prints in the mold system. Cores may be sand, ceramic, or metallic in composition. Non-metallic cores are not reusable and can be removed from the casting by dissolving in caustic media or by mechanical agitation. This ability to easily shape the hollow interior of a part is a unique and valuable advantage. The pour cup is the funnel-like opening into which the molten metal is poured. The sprue is the portion that connects the pour cup with the runner. The runner is the channel through which the molten metal flows through the mold. The gate is the portion of the channel in a mold through which molten metal directly enters the mold cavity. There are 4 main casting processes: investment casting and sand casting, and less frequently used for aircraft engine parts, permanent mold casting and die casting. Because of certain unique advantages, the most common means of casting parts in manufacturing aircraft engines is investment casting. At foundries such as the Arwood Corporation in Groton, Connecticut, aircraft engine parts are cast for General Electric with great precision using this process. Investment casting uses a mold produced by surrounding an expendable pattern with a heat-resistant ceramic material. The first step is the production of a master pattern die. Here, a special automated die for a combustor swirler is being machined. Investment casting dies are usually made from low melting point metal or from steel. When steel is used, the cavity is usually machined directly in the die. If low melting point metals are used, the dies are cast using a master pattern. Next, low-cost expendable wax patterns are produced. The master die is closed and heat-softened wax is injected into the die under pressure. When the pattern has hardened, the die is opened. The pattern is removed and excess wax cut off. An exact wax replica of the part is now available. Several of the wax patterns are attached to a central sprue with runners and gates by means of heated tools and melted wax. This allows a number of parts to be produced from a single mold. In some cases, several pattern pieces can be united to form a complex single pattern that, if made in one piece, could not be withdrawn from a master die. The cluster is coated with a ceramic material which has great heat-resistant properties, called refractory. A first or prime coat acts as a base for the mold and must withstand attack by the molten metal. Here, the fine refractory is suspended in a liquid binder, or slurry. The slurry-coated cluster is then stuccoed with a coarser, dry refractory. This adds strength to the initial coat and prevents cracking of the mold by retarding shrinkage during drying. After the cluster dries, a second coat of refractory is applied to back up the first. This is generally not as thick as the first coat and is usually different in composition. Refractory thickness and consistency is varied according to the particular application. Clusters are thus dipped an additional number of times to form as many layers as is necessary to achieve adequate mold thickness and consistency. Each coat is stuccoed with a dry refractory. The completed shell is called the investment. When the investment has hardened, the mold is placed upside down in an oven or high-pressure steam autoclave. With the ensuing high pressure and temperature, the wax pattern is melted and permitted to run out of the mold. A very complex pattern can therefore be removed from a mold without the mold having to be made in 2 or more sections in order to be opened. This enables more complicated shapes to be cast with the investment process than with most other processes. De-waxed molds are often fired a second time to completely remove all wax residues and to impart full strength to the ceramic mold. Some of the wax is collected in the bottom of the oven and recovered for future use. Molten metal is then poured into the mold. The mold is preheated to assure that the metal will flow more readily to all thin sections. This procedure also gives better dimensional control because the mold and the metal shrink together during cooling. After the metal cools, the casting is removed from the mold. This is done by breaking the brittle mold away from the casting. The part now undergoes a variety of finishing and inspection operations. The parts are separated and the sprues and runners cut off. Excess molding is removed by an automatic tumble blast operation. Here, small sand-like particles of aluminum oxide are placed in a barrel along with the parts. When the barrel is rotated, the particles abrade the part surfaces, mechanically removing the molding material. This operation can also be done with various other sand or grit blasting techniques, depending on the design of the part. Any remaining gates are machined off using a secondary operation. With combustor swirlers, the molten metal enters the mold cavity through channels in the center of the swirler. These gates are removed on a drill press using a hole saw, which can cut excess metal out of the round interior of a casting. Other methods, such as grinding and belt sanding, can also be used on certain parts when the gating is more accessible to machining processes. Sharp edges are removed with deburring operations. In some cases, the finished parts are heat treated in order to acquire better metallurgical properties. The final casting is then inspected using a variety of different methods: visual inspection, X-ray, and fluorescent penetrant inspection, which uses an iridescent dye that seeps into defects, which are then illuminated with an ultraviolet light. Though investment casting is generally more expensive than other casting processes, the use of an expendable mold has many advantages. Due to their non-symmetric or intricate shape, many parts cannot be cast by other processes. Oftentimes, these shapes can be cast using investment casting much more economically than they can be machined. Since no mold material must be packed around the pattern, very thin sections can be cast. Very close tolerances and good internal quality can also be maintained. Due to the nature of the ceramic mold, excellent surface finishes can be produced as well. Many of the metals used in making aircraft engine parts have melting points greater or equal to the melting point of the metals used in making the molds for permanent mold or die casting. In these cases, thermal shock can cause cracking of the mold. Investment casting presents no such problems. This unique combination of qualities makes investment casting ideal for the manufacturing of high-stress aircraft engine components. Another type of casting frequently used in making aircraft engine components is sand casting. This involves using sand as the mold material. At the Mead Foundry in Bedford, Massachusetts, sand casting is done for a wide variety of parts. First, a pattern, along with forms for sprues and runners, is placed in a metal box made in two parts, so that each half of the mold can be produced separately. This allows the pattern to be removed. Talcum powder is sprinkled around the pattern to prevent sticking. Pieces of iron called chills placed within the mold cause faster solidification of the molten metal in certain sections. This creates superior properties in these high-stress areas. Next, sand is placed around the pattern. This sand is specially formulated so that it will quickly harden after production of the mold is finished. This allows for maximum efficiency in production of cast parts. Special asbestos sleeves insulate sprues to prevent the sprue metal from solidifying before the metal forming the part solidifies. This reduces shrinkage defects. Additional sand is shoveled in to fill the mold and back up the initial molding material. The sand is packed down firmly to assure that all areas are filled. Excess sand is then removed and a smooth, level surface is produced. In this instance, holes are poked through the mold to allow compressed gas to enter the mold material. The sand is hardened by pumping carbon dioxide into the mold through the holes. The CO2 reacts with chemicals in the sand to produce almost instant hardening of the entire mold. The mold is now turned over and the other side processed in the same way. The pattern is then removed to leave a cavity of the proper form. A core of the proper shape is placed inside the cavity. Molten metal is now poured into the pour cups and makes its way into the mold cavity through the sprue and runner system. The casting is removed from the mold by breaking the mold apart by hand and extracting the finished part. In some cases, the sand is reusable, while in other cases, such as the CO2 set mold, it is discarded. In sand casting, part cost is low, and tooling cost is low. But since a new mold must be produced each time, production rates are also low. Also, the sand mold provides a poor surface finish and only fair internal quality. Permanent mold casting is a process in which the mold is made from various metals, making it relatively reusable. This process is used less often than investment in sand casting in making aircraft engine parts. As in sand casting, metal is poured into the mold through a system of sprues, runners, and gates under gravity. The mold must also be in at least 2 pieces, and the pattern must be shaped so that the part can be withdrawn when the mold is opened. Die casting differs from permanent mold casting in that the metal is forced into the mold under pressure and held under pressure during solidification. Because casting involves melting and resolidifying metal, castings are subject to a number of defects which can affect the internal quality of a part. Shrinkage voids are holes produced in a casting as the result of contraction during solidification from the molten state. These voids may be small and uniformly dispersed through an area of a casting, or clustered into one or more large cavities within a casting. Gas porosity is the presence of small holes which are formed by gas trapped within the solid metal during solidification. Generally, the porosity is round or oval and is caused by the presence of hydrogen in the molten metal. Cracks are open linear discontinuities, which can be produced in castings due to solidification stresses or mechanical damage. Inclusions in castings are pieces of foreign material which are trapped within the casting during solidification. The foreign material is generally non-metallic in nature and is less dense than the metal being cast. Common sources of inclusions are pieces of mold material, such as sand, crucible material, and metal oxides, or slags. Unacceptable surface finishes can be caused by poor mold building practice and excessive process temperatures. Non-fill, often called a misrun, is a condition in which the casting shape is not completely filled out by the molten metal. Generally, this occurs on thin sections where the metal solidifies too quickly. Dimensional discrepancies can result with insufficient tolerances or improperly applied shrinkage allowances. A parting line is a plane on a pattern or a line on a casting corresponding to the separation between the top and bottom portions of casting tooling. There are many advantages to casting over other processes in producing parts. Oftentimes, complex shapes can be cast much more cheaply and easily than machining. It is also more precise and requires less subsequent machining than forging. There is also less wear on tooling than in forging. On the other hand, properties are generally poorer with castings than with forgings. Though high temperature stress rupture qualities are better, important room temperature fatigue properties are not as good. Here are some typical examples of the many different aircraft engine parts that are produced by the casting processes that have been described. Casting consists of pouring molten metal into a mold of the proper size and shape and allowing it to solidify. The mold system consists of a crucible, pour cup, sprue, runner, gate, pattern, and core. The most common casting processes used for making aircraft engine parts are investment casting and sand casting. Investment casting uses a mold produced by surrounding a wax pattern with a ceramic material and then melting out the pattern. Sand casting uses a mold in two halves, produced by packing sand around a pattern and then removing the pattern by taking the mold apart. Permanent mold and die casting involve reusable metal molds. In comparing the various casting processes discussed, part cost is always an important factor to consider. We find that part cost is high in investment casting, but low in sand casting and permanent mold casting, and very low in die casting. Tooling cost is another factor to be considered. Tooling cost is medium in investment casting, low in sand casting, medium in permanent mold casting, and high in die casting. The melting points of molds used in permanent mold and die casting are often too close to the melting temperatures of the metals needed for aircraft engine parts. Therefore, these processes are not used extensively in this industry. Production rates are medium in investment casting, low in sand casting, medium to high in permanent mold casting, and very high in die casting. Surface finish is good in investment casting, poor in sand casting, fair in permanent mold casting, and good in die casting. Internal quality is good in investment casting, fair in sand casting and permanent mold casting, and poor in die casting. The good internal quality and surface finish are two reasons why investment casting is the casting process most often used in making aircraft engine parts. Defects that often occur in castings are shrinkage, porosity, cracks, inclusions, poor surface finishes, non-fill, dimensional discrepancies, and parting lines. Casting, an ancient process still used for meeting the needs of high technology in a modern world.